Okay guys, in this video we're going to be looking at a formula we use often when we talk about compounding, especially in financial accounts. And so we're going to be looking at specifically growth and kind of tying it into what we've seen thus far. And so really quickly as a recap, we've been looking at exponential growth and decay models of the form y equals ab to the x power, where our a is our initial value and our b is kind of like our growth or decay factor here. In our last video we looked at how we could rewrite this as some starting amount or a principal amount times 1 plus or minus some rate to the t. And so this model evolved into this model you see here. In this video we're going to evolve this model one more time into these models that you see here on the left. And so I want you to understand that when we write that the amount here, and I'm writing this formula here, is equal to what I started with times 1 plus r over n to the nt, we still have an initial amount here. And we still have a base that is being raised to a power, and we still have some power that we are raising this to. It's just that this is a little bit more explicit in terms of where we need to put things, because it's talking about specifically a financial situation and how things compound that way. So we are going to use this particular formula that you do need to have memorized, that you do need to be able to recall in order to evaluate how much money would I have at a given amount of time if I started to compound it. So some quick things. This A here is going to represent the what is remaining of the principal amount or at a time t. So what is remaining of the principal amount at time t is our A value there. P is our principal amount, so specifically at time 0. R is the rate, where R is a decimal. T is the time in years. And then lastly, we're going to say that N is the number of times per year that the principal compounds. So of all the things in this, besides typing it in a calculator, N is going to be the one value that we want to make sure that we talk about. So really quickly here, if N is the number of times each year you compound, then often you're going to see words like annually, semi-annually, weekly, daily, these kind of things. The real question is, well, how many times a year would it compound if it compounds annually? And the answer there would just be that N would have to be 1 because it's compounding once a year, whereas semi-annually, every 6 months would mean it compounds twice a year. Biannually, this is kind of weird. This means once every 2 years. So what would that mean about every year? Well, that would mean that it compounds a half a time each year, which is crazy, but that's how our N value would be. Quarterly just means 4 times a year or every 3 months. Monthly is going to be 12 times a year. Weekly is going to be 52 times a year. And daily, of course, is going to be 365 times a year-ish. So looking at a situation where I might want to use this formula and how I put it in a calculator, let's consider this. It says you invest $5,000 in an account that pays 6% interest quarterly. Identify the pertinent information and then write a model for the amount of money y over time x. And so when we look at this here, we say our principal amount is $5,000. In terms of our rate, we have a 6% rate, and so we're going to say 0.06. And then in terms of n, well, this was quarterly. So quarterly, looking up here, is 4 times a year. We say 4 times a year. In terms of our model, we're going to say that the amount of money we have, y, which is what I was using a for previously, we can use y in its place. Y is equal to what I started with, so we have this $5,000. And this time we're going to multiply by not just 1 plus the rate, but 1 plus the rate over n. So we get the rate here, which is 0.06 over 4 on the inside of here. And then we're going to raise this to the power of n times t, where in this case n is 4, but t is just general. Remember that we were writing a model, and when we write a model, we don't specifically plug in anything for t or y. We just say this would represent what's happening to my $5,000 over time t. So now, what I'd like to do is use this model to predict the amount of money in the account after 5 years. And I want you to realize that what I've just given us is a time, also 15 years. So we're going to go plug these in for our times, and we're going to go evaluate our function. So with respect to the first one here, we say at 5 years afterwards. Let's write this out. We would have the 5,000 we started with times 1 plus 0.06. I'm going to try to clean that up for us here. 0.06 over 4 to the 4 times, and I'll even put this in a different color here, 5. So we're actually going to go plug in that 5 there. We should get an approximate value. So part of this is I just want to show you best practices for typing this in. So we're going to go ahead and put in our 5,000 here on our calculator, but just put a beginning parenthesis, and we'll hit 1 plus point. Let me fix this here. There we go. 0.06 divided by 4, and then end our parenthesis there. And so the neat thing here is I don't need individual parentheses around the 0.06 over 4 on the inside, because in terms of order of operations, my calculator is going to carry out this division in here before it adds it to my 1. So we can leave it this way. We're also going to raise it to a power. Now, it is important that you put a beginning parenthesis here, because this 4 times 5, I know it's 20, you know it's 20, but if you wrote, let's put it this way, if you wrote 4 times 5, your calculator would actually take this inner parenthesis portion, do the division, add it to 1, and then raise it to the 4th power, because it's going to do exponents first, and then take that answer times 5, when in reality what we want to do here is we want to say, no, do the 4 times 5 first, and then we're going to raise this base to that power. So doing this, I get this value here. I'm going to go ahead and hit second enter, and I'm going to go back and insert a 1 here in front of my 5 and get my 15 years later. But we get two values here, the first one being 6734.28. So 6734.28, and this is in dollars. And then if we were to do this 15 years later, it would be 5,000 times 1 plus 0.06 fourths to the 4 times, and in this case we want 15 units of compounding. So we get y is approximately here, looks like 1221610, 12216.10, and this is in dollars. So we'll use this formula when it comes to compounding interest. Any other models, though, that we use, we use a simple model, which is just 1 plus r, and then take that to the t. Cheers.